Hey folks, my name is Nathan Johnston, and welcome to Lecture 33 of Advanced Linear Algebra. The goal of today's lecture is to introduce two new matrix decompositions based on positive semi-definite matrices. The first of them is called the principal square root of a positive semi-definite matrix, and the other one is called the polar decomposition of a matrix. But before we can get to those theorems, we need sort of a helper theorem that's going to get us most of the way, that's going to do most of the heavy lifting in proving those theorems. So that's what we're going to start off with. This theorem 8.7 here, it's the helper theorem that's going to get us most of the way towards the two theorems we actually care about towards the end of this lecture. Okay, so what is this theorem 8.7? Well, it answers the question of what do the different decompositions of a positive semi-definite matrix look like, okay? And what I mean by that is, remember, every positive semi-definite matrix A, it can be written down in this sort of decomposed way, B star times B, okay? Well, that matrix B there is very, very not unique. For example, okay, if I replace B by U times B, where U is just any old unitary matrix, well, then what happens? If I compute, if I say C is U times B and then I compute C star C, what's going to happen is, well, if I just plug in UB for C, then I'm going to get UB all star times UB. And then I just simplify this down using all of our usual matrix multiplication tricks, right? So stars on both of them and the order swaps. And then on the middle here, I've got a U star U. Well, that's just the identity matrix because I chose U to be some unitary matrix. Okay, so I see that C star C ends up being the exact same as B star B, which is just A, right? Right, so the point of this is if I have one decomposition of A, if I have one way of writing A as B star B, well, then I can find another matrix that also works, another decomposition of it. I can find a C that decomposes it in the exact same way. In fact, I can find lots of C's because there are lots of unitary matrices I can choose. I can choose any unitary matrix I want. And doing left multiplication by that unitary matrix will get us another decomposition of A. Okay, so what this theorem 8.7 says is, well, actually, that's how you get all possible decompositions of a positive semi-definite matrix. There are no others, okay? So let's read this a little bit more formally here, okay? So suppose you're working over the real or complex numbers so that you have positive semi-definite matrices in the first place. All right, and then, well, it says that two different matrices B and C, they both provide positive semi-definite decompositions of the same matrix if and only if there's some unitary matrix relating them, if and only if there's some unitary matrix such that C equals U times B. Okay, so not only does left multiplication under a unitary matrix give you another positive semi-definite decomposition of this matrix, but actually you get all positive semi-definite decompositions of the matrix in this way. Okay, there always is a unitary matrix relating any two matrices that decompose the same positive semi-definite matrix. Ugh. Okay, so that's sort of the technical theorem that we're going to need just to help us prove the two theorems that we actually care about. We're not going to prove this theorem 8.7. Well, actually, we proved sort of half of it in a sense. We proved the if direction. We proved that, if C equals UB, then B star B equals C star C. So we proved that direction, but we did not prove the only if direction. We did not prove the existence of the unitary. All right, and the reason is just it's super long and technical. We leave it to the textbook. Okay, but we are going to make use of this theorem, okay? So now that we know all PSD decompositions are relayed via unitary like this, well, now we can ask the question, okay, great. These PSD decompositions, they're not unique, but can we hope to find a simplest one in a sense, okay? So out of all the matrices B, such that A equals B star B, can we find a simplest one? Can we find a particularly simple B? And there are a couple of different ways of answering this. There are a couple of, like, depending on exactly what you want, your answer for, well, what's a simple matrix might be a little bit different. But one particularly nice answer is that, well, you can always choose B to be positive semi-definite, actually, okay? If A is positive semi-definite, you can actually choose this sort of decomposed part, B, to also be positive semi-definite, okay? And furthermore, there's exactly one positive semi-definite matrix B that you can choose there. Okay, so we give that matrix a name, we call it the principal square root of A, okay? And that's what this next theorem is, okay? So again, suppose you got some positive semi-definite matrix, then there exists a positive semi-definite matrix P such that A equals P squared, and I mean, P squared, of course, is the same as P star P, because P is positive semi-definite, so in particular it's Hermitian. P star is just P itself. All right, so there exists a positive semi-definite choice here, and furthermore, it's unique. Okay, so we give that unique positive semi-definite matrix a name. We call it the principal square root of A. Okay, and in a sense, this is nothing different than what we've done before with square roots, right? We've already talked about how to take square roots of a matrix, The only really new thing in a sense here is that, well, if you take a square root of a positive semi-definite matrix, well, again, there might be a whole bunch of different square roots, but there's exactly one that is positive semi-definite. All right, so let's go through the proof of this theorem, or at least proof of part of it anyway, just to remind you of how square roots and these diagonalization arguments work, okay? So the way to find a square root, to show existence of a positive semi-definite square root, is, well, we just do our usual diagonalization thing. Break A down into a spectral decomposition, which is U d U star. Because it's positive semi-definite, we can do that. And furthermore, we know the diagonal entries of D are all bigger than or equal to 0. Okay, and then we're just going to define something that looks like the square root. Like our sort of first guess, hopefully at this point, would just be, well, let P be the thing that has sort of the same spectral decomposition, except the square roots of those diagonal entries in the matrix D. Okay, so root D is just the entry-wise square root of D itself. Okay, so you're just taking square roots along the diagonal. Okay, and let's just check that, yeah, let's check that P actually is a square root of A. So in other words, let's check that P squared equals A. Right, and the way you do that is you just multiply this decomposition of P times the decomposition of P. And then in the middle here, you're going to have a U star U. Well, that just cancels out, becomes an identity matrix. You're left with U root D U star. And of course, the root D just becomes a D. And then you just got U d U star. And of course, that's just equal to A, which is what we want. So P squared really does equal A. All right, so this matrix P, it is a square root of A. Okay, and furthermore, it's positive semi-definite because D had non-negative real entries along its diagonal. So root of D also has non-negative real entries along its diagonal. So root D is, you know, positive semi-definite, and conjugating by unitary matrix, still positive semi-definite. All right, so yeah, there exists a positive semi-definite square root of A. Uniqueness, well, we're going to leave it to the textbook. Sort of the rough idea is that as long as your matrix is normal, sort of its eigen decomposition completely determines the matrix. So, I mean, you know, any square root of A, well, its eigenvalues are going to have to be the square roots of the eigenvalues of A, and its eigenvectors are going to have to be the same as the eigenvectors of A, and then you can just sort of, you can roughly just do this argument backwards with some technicalities in it, okay? All right, so, well, let's go through a computation here just to make sure that we're understanding what's going on. Let's find a principal square root of a matrix. And as a bit of a notation, I mean, we often use just this sort of standard square root notation, okay? We often say that P equals, you know, just square root of A, okay? It is, because, well, now there's basically just one of them, okay? If we understand that we want the principal one, the positive semi-definite one. All right, so let's find the principal square root of this matrix, okay? And before we can do this, I mean, we want to make sure that this matrix is positive semi-definite, but fortunately it is. It's diagonally dominant, right? Diagonal dominance implies positive semi-definiteness. All right, so it's PSD, so no problem. We can go forward, and the way that you find the principal square root is you do a spectral decomposition, then you square root the entries along the diagonal matrix D, and then you throw things back together. Okay, so first, do eigenstuff. Find a spectral decomposition. So you find the eigenvalues of this matrix. Turns out they're 5 and 20. Okay, I'm skipping over a calculation here. You know how to find eigenvalues. You know how to find eigenvectors too. Okay, corresponding eigenvectors to the eigenvalues are 5 and 20. Well, they're 1 minus 2 and 2, 1, okay, respectively. So like 5 and 1 minus 2 is an eigenvalue-eigenvector pair, and 20, 2, 1, that's an eigenvalue-eigenvector pair as well. All right, that's enough to get us the spectral decomposition. Throw things into a diagonal matrix D, okay, so you throw the eigenvalues down the diagonal, and then throw the eigenvectors into a unitary matrix here. Be careful to renormalize them so that it's actually a unitary matrix. You don't just want any eigenvectors as your columns, you want unit eigenvectors as your columns. So 1 minus 2, that's our first column, except you have to divide by its length. Its length is root 5. Similarly for the next column, 2, 1, that's our next column, divide by its length, which also happens to be root 5. All right, so this is the unitary matrix in the spectral decomposition. Next up, to find the square root of A, all you do is, well, you leave U alone and you take square roots of the diagonal entries in D. Okay, so the square root of A, well, it's just going to be U root D U star, which, well, you just throw everything together. Okay, so I'm gonna leave U on the left alone, and I'm going to leave U star on the right alone. So here's U star, and I've just pulled the two 1 over root 5s out in front as a 1 over 5. And then in the middle here, it's just I'm taking the square root of the entries in D. So I do root 5 at the top left, and root 20 at the bottom right, which is just the same as 2 root 5. Okay, and then you just multiply all that crap together, and you get 1 over root 5. 9226, and then it's straightforward. I mean, that's our final answer, but if it makes you more comfortable, it's straightforward at this point to double check that yes, this matrix really is positive semi-definite, and if you square it, you get that matrix A that we started with. Okay, so that's the principal square root of a positive semi-definite matrix. Now what we're going to do with that is we're going to use the principal square root of a positive semi-definite matrix to prove a new matrix decomposition that applies to arbitrary square matrices. Okay, so this decomposition is called the polar decomposition, and what it says is if you have any old square matrix, has to be real or complex again so that we can talk about positive semi-definiteness in a second, well, then you can break that matrix down into a unitary matrix times a positive semi-definite matrix. Okay, and we'll talk about sort of how to interpret this theorem in a second, but for now let's prove it. Okay, let's see where this comes from. How can you break every matrix down in this way? Okay, it's just going to follow from the principal square root of a matrix really quickly. All right, so here's the setup. Instead of considering A itself, let's consider A star A, and we're going to note that, hey, A star A, well, that's of that special form that every positive semi-definite matrix is of. Okay, so we know that this is positive semi-definite. Okay, well, if it's positive semi-definite, then we know from the previous theorem that it has a principal square root. Okay, so I'm going to just let P be that principal square root. P is the principal square root of the positive semi-definite matrix A star A. Okay, great. All right, well, let's notice now that if I compute P star P, well, that's of course just P squared because P is positive semi-definite and therefore Hermitian. But P squared is equal to A star A, right? The point of P is that it's principal square root of A star A, so squaring it gets you A star A. Okay, but now look at what we've got. We've got P star P equals A star A. And wait, theorem 8.7, the first theorem that we looked at in this lecture, told us when things like this can happen. How can you have some matrix star times that matrix equals another matrix star times that matrix? Well, the only way that can happen is if there's some unitary matrix relating them. If these matrices are related to each other via left multiplication by a unitary matrix. Okay, so we just invoke that theorem and we see that, oh yeah, there exists a unitary matrix U such that A equals U times P. Okay, and then we're done. That's it. That's exactly what we wanted. We took an arbitrary matrix A and we showed that there exists a unitary such that, you know, A equals U times some positive semi-definite matrix. All right, so that's it. Let's think about how to interpret this theorem now, though, okay? Because it has a really nice geometric interpretation. If you think back to complex numbers, this is completely analogous to something that you do with complex numbers, right? This matrix, the square root of A star A in the polar decomposition, that can be thought of the matrix version of the absolute value of a complex number, right? The way that you compute the absolute value or magnitude of a complex number is you take Z, you multiply it by its complex conjugate, and then you square root at the end of the day. Well, that's basically what we're doing here. We're multiplying A by its conjugate transpose and then square rooting at the end of the day. Okay, and when you do that, you get something positive semi-definite, just like when you do it over here for complex numbers, you get a positive real number. Okay, and furthermore, the polar decomposition itself, so this fact that you can write every matrix as a unitary times positive semi-definite, it generalizes the polar form of a complex number. Okay, so remember every complex number Z, it can be written in this form, Z equals R times e to the I theta, okay? Where R, you know, that's just the magnitude of Z. It specifies how big or how far away from zero the complex number is. And this e to the I theta, it specifies sort of the angle of the complex number, right? E to the I theta, that's some number on the unit circle in the complex plane. Okay, well now the way to think about this, the way that this sort of generalizes to matrices is that, well, we can write it as a positive semi-definite matrix times a unitary matrix, right? In the 1-by-1 case, positive semi-definite matrices are exactly non-negative real numbers. And in the 1-by-1 case, unitary matrices are exactly numbers on the unit circle in the complex plane. All right, so geometrically, what's happening here, again, if we just draw the complex plane here, well, if you have some number in the complex plane, you can break that down by sort of into sort of an angle and a length. Okay, this is the same as polar coordinates in R2, if you've seen polar coordinates. Okay, so the way to do this is, well, okay, so it's an angle of theta up from the real axis or the x-axis. I'm going to draw on the unit circle here. And then, well, this spot here, this e to the I theta, that's the number that's up at the same angle theta, but at a distance of 1. Okay, it's just on the unit circle. Okay, so that piece sort of specifies, well, what angle is Z at? You know, what's the rotational piece of Z? All right, whereas the length of this line, that specifies, you know, how big is Z? How far away is it? Okay, and you can always break a complex number down into its angle and its distance. Okay, and for matrices, this polar decomposition is saying you can basically do the same thing for matrices. You can break every matrix down into sort of a rotational piece. Remember, we think of unitaries as rotations, and sort of a length or a stretch in the positive direction. And that's sort of the way to think about positive semi-definite matrices. They just sort of stretch things out. They blow them up, but they don't rotate too much, okay? They don't really change orientations of vectors all that much. Okay. So that's how to think about the polar decomposition. We don't know actually how to compute this yet, so we can't go through an example of actually computing a polar decomposition, because if you try to trace through the proof, we have this sort of mysterious step where we see, oh, there exists a unitary such that this happens. And well, where does the existence of that unitary come from? Well, unfortunately, we skipped a proof earlier in this lecture. We skipped the proof of theorem 8.7, so I can't tell you where that unitary comes from. I can't tell you how to construct it. We're going to see a different way of constructing a polar decomposition next week. Okay, and now we're going to close out this week and this lecture just sort of on another sort of hand-wavy philosophical note, okay? We're just going to sort of try to tie together our intuition for some things that we've learned over the last couple weeks. Okay, so to start off with, I'm going to just sort of draw here a Venn diagram of different families of matrices that we've seen over the last couple weeks. Okay, so starting off with just the space of all n by n complex matrices, there are all sorts of important families of matrices inside the set of n by n complex matrices. Probably the biggest important set that we've seen is the set of diagonalizable matrices. In some sense, most matrices are diagonalizable. Almost all of them are. Okay, so there's the set of diagonalizable matrices, and within that set, there's the set of normal matrices, right? Every normal matrix is diagonalizable because the spectral decomposition is a special case of usual diagonalization. It's the special case where it's diagonalizable via a unitary matrix rather than just an arbitrary invertible one. All right, so normal matrices are all diagonalizable. And then within the set of normal matrices, well, there's the Hermitian matrices, for example. And there's also the skew Hermitian matrices, for example. And I've drawn them like this, just barely touching for a reason. There's only one matrix that's both Hermitian and skew Hermitian, and that's exactly the zero matrix. Okay, so that's the unique matrix that's in both of these sets here. Okay, another important family of matrices that we've seen are the unitary matrices, and I've sort of drawn it as a ring here. I mean, there's not a great reason for this, but I'll sort of justify it a little bit in a second. I roughly think of the unitary matrices as like a circle. It's not just a circle, though. It's got a little bit of stuff inside of it. You know, it's maybe, you know, it's got a bit of wiggle room on the inside or something like that. I don't know. That's roughly how I think about the unitary matrices anyway. Okay, so, and again, these are all normal, so it's inside the normal set, and there are some Hermitian unitary matrices, and there are some skew Hermitian unitary matrices. Okay, and we've also learned about the set of positive semi-definite matrices. These are all Hermitian, so it's inside the set of Hermitian matrices. Okay, and again, I've drawn things barely touching here for a reason. Okay, there's exactly one matrix that's both positive semi-definite and unitary, and it's the identity matrix. That's the only positive semi-definite unitary matrix out there. All right, so those are the relationships between the various families of matrices that we've seen over the last couple of weeks. And I'm going to draw one more toy picture of all of these families of matrices, this time sort of as families of matrices analogous to sets of complex numbers. And again, this is just for intuition building. This isn't anything rigorous. It's just to help you sort of keep track of how to think about these matrices. Okay, so I'm going to draw the complex plane here. I've drawn the real number 1 and the real number 0 on there. Okay, and here's your real axis and here's your imaginary axis. Okay, and I'm going to think about everything in the complex plane as analogous to some matrix or some family of matrices, right? So we think of the number 1 as analogous to the identity matrix. The identity matrix is sort of the matrix version of the number 1, because if you multiply any matrix by the identity, well, it doesn't change. Just like if you multiply a number by 1, it doesn't change. All right, and we think of course, the number 0 as analogous to the matrix 0. All right, we think of the real axis as sort of analogous to the set of Hermitian matrices. And there are a bunch of ways that you can justify this, but maybe the one that we've seen is that, well, remember Hermitian matrices, those are exactly the normal matrices that have all real eigenvalues, right? Every eigenvalue of a Hermitian matrix is real, okay? Similarly, we think of the imaginary axis as analogous to the set of skew Hermitian matrices. You can check, we didn't prove this, but it's sort of a straightforward exercise to show that every skew Hermitian matrix, it has all purely imaginary eigenvalues. So that's one way of justifying that. Another way of justifying these two intuitions here, or these two ways of thinking about Hermitian and skew Hermitian matrices is, well, every complex number can be written as a sum of a real matrix and an imaginary matrix, right? This is sort of the naive way of writing down a complex number. Like you would have like 3 plus I over here. Well, that's a real number 3 plus an imaginary number I. Similarly, every matrix can be written down as a Hermitian matrix plus a skew Hermitian matrix, okay? So, and it's even called the same thing. These are called the Cartesian decomposition of a complex number and the Cartesian decomposition of a matrix. Okay, so thinking about matrices in these ways is very useful, okay? Another useful sort of analogy to keep in mind is the unit circle here, right? The circle containing every complex number with magnitude 1. Well, we think of that as analogous to the set of unitary matrices. And one way to justify that in your head, well, every unitary matrix, you can check that its eigenvalues all live on the unit circle. They all have magnitude 1. Another way to think about it is if you take a complex number and you multiply it by something on the unit circle, it just rotates it, right? It doesn't stretch it or shrink it at all. It just rotates it by whatever that angle was. Well, similarly with unitary matrices, we think of unitary matrices as rotations, right? They just rotate things, but in a higher dimensional space. And then one final one is the positive real axis, okay? So not the entire real axis, but just the positive, or maybe even just the non-negative real axis. We think of that as analogous to the positive semi-definite matrices. Remember, I've been trying to drive this point home a little bit. We think of positive semi-definite matrices as the matrix version of, non-negative real numbers, okay? And I mean, yeah, like the positive real axis, it lives within the whole real axis, and PSD matrices live within the set of Hermitian matrices, and PSD matrices, furthermore, I mean, all of their eigenvalues do live on this positive half here, okay? And we sort of think of them, if you multiply one of them, it just stretches things in the positive direction, just like if you multiply by a positive real number. All right, and again, like this is just a toy picture, but thinking about the things in this way is useful because you can sort of get a sense on how these different families of matrices interact with each other. For example, this picture suggests that, hey, like if we look at the intersection of two of these sets, like the intersection of the unit circle and the positive real axis, I notice that, hey, there's only one number there. It's the number 1. The only number that's on the unit circle and positive, it's 1. Well, it turns out that the same thing happens for matrices. The only matrix that's both unitary and positive semi-definite, well, it's the identity matrix, okay? There's only one of them. Okay, so even though it's a toy picture, it's useful for building intuition. It's a toy, but it's not too wrong. It's reasonably good. All right, so that will do it for today's lecture. I will see you soon for week 9's notes and lecture 34.